All right, a couple things we wanted to possibly go over is why don't you go ahead and open these wonderful textbooks to, where would be a good place to start? Just so we kind of get a handle on how much you've actually learned even just with this chapter so far. Page 386, I think, rather than looking at what we've done so far this semester, if we're going to try to get this wrapped up in a short amount of time, that just wouldn't be possible then. Okay. So when you're looking at these reactions, when we're dealing with these alcohols, yes, it's important to know, is it a primary or is it a secondary? In both of these cases, okay, everyone would agree that these are both primary alcohols. No one's going to argue with that. But with what we spent time on yesterday, can anyone look at that and see what the difference is? Yes, there's two differences between what we've learned, and then there's one difference between here, and it's the catalyst that we see. The temperature is what I mean. Oh, we didn't. Okay. So, but my main point is, yesterday we spent time on with oxidizing agents. And we spent a little bit of time on dehydration reagents. That's what sulfuric acid is. It dehydrates rather than oxidizes. Okay. And then also, when these tend to be dehydrated, okay, depends upon the temperature range that this happens at that alters what you're going to form over here. So on page 386, just happens to be a coincidence that they're showing you ethanol there. And that, what do you see in that sample 13.6 on the bottom there? When you dehydrate something, we know you are taking out water. No one would argue with that. And that's what they're illustrating here. You lose a hydrogen in your OH group. Okay? Then, and I think it was maybe a little difficult to possibly catch on to the idea of, yes?
Yesterday we only did the oxidizing, or whatever, of primary and secondary. We never got through the last one that you drew up there.
Yeah, it's because tertiaries don't oxidize. Yeah. Are you talking about the naming of it?
No, you had one written down that was just like that, but we never went through them.
Oh, okay. We will get to that. Okay. So with this, then we turn the page to 388. So in the example 13.8, what you see down there on the bottom, okay, when you look at that, that type of alcohol is what instead? On the bottom of 388, you can even, it shows you even in the solution, okay? You're starting with what kind of alcohol? It's actually 3-hexanol. Okay. Unfortunately, we're just not quite communicating here. Okay. What we see, we're talking about this guy right here. What kind of alcohol is that? We don't want to name it, just what kind. You got three choices. It's either tertiary, a primary, or a secondary. It is a secondary alcohol. That's right. And how do you know that? You're right, but how do you know that it's a secondary alcohol?
Because the carbon that it's connected to connects to 2.
Yeah, that's right. Okay. And I don't think it's a good idea to look at that and say, as long as it's not attached to the end, that it's a secondary alcohol. That, I would not advise doing that. I would advise going by how you had explained it. That would be a better way of looking at it. When that OH group is attached to a carbon that's attached to 2 more, that gives you a secondary alcohol. Now, those also dehydrate, okay? And they'll give you 2 products as well. We didn't spend time on that. We're just mainly concerned with going through the primary alcohol. And when we do that, okay, for instance, we see here, we can just keep this really short. So we can use this, oops, what am I doing? I'm giving you a product rather than an example. Okay. And there again, we know that this is the secondary alcohol because that carbon's attached to two more. So if we dehydrate that then, plus H2SO4, we're not concerned about the temperature range. Okay. When something gets dehydrated, what happens? You're losing what? When something gets dehydrated, it's losing water, okay? So when this dehydration reagent works on this, okay, this will disappear, okay? And then left or right? Okay? So there we got our formula for what now? A hydrogen and an OH. Yeah, H2O, or water. So that's dehydrating. What we're trying to illustrate here is now why are we not writing anything down there? Because these boxes, that water got stripped off of there. And you put that double bond in there just like what you said. The difference with what we see here is how do we know that it's always going to put a double bond there? We don't. So that's why we say you get two products. Okay? Because remember, I said left or right, correct? So what we would see happening is I can put that in a different color. So now, the first one you said right. We're still going to take this guy off, but now we're going to go left. So notice these are both gone down here now. Okay? When it comes to dehydrating secondary alcohols, you get two products. Because when it dehydrates, the double bond may go to the right of the hydroxide, or it may go to the left of the hydroxide. So you get two products. Okay. I was under the presumption that we had gone over that. We had not. I'm taking that. Okay. Does that seem awful? Hopefully it's not too bad. And I think maybe with practice, it will hopefully get a little better. And that's why you also have those flow charts to go with it.
Are you gonna get like something different if the degrees and the arrows and highlights are different?
For this one here?
Yeah.
No, we're not worried about a temperature range. That only occurs with primary alcohols. Yep. Yep, yep. Nothing like covering all the bases. Okay, can we go ahead and erase this? There's no major product, there's no minor product, okay? You're just forming two of these because like we said, these probably form in equal rates. When this OH and that hydrogen get taken off, that's how we get to here. This OH and that hydrogen get stripped off, that's how we get to this one. So you would get butene. This one's butene, and this one's what? This one's butene. This one's also butene, but it's just a little different. It's 2-butene, right, because you need to account where that double bond is. Yep. That is correct. Okay. Okay. So Can we erase this? Okay. All right, I don't like throwing that because my apologies, I thought we went over that. So sometimes that just happens. Because we did, I know what we did yesterday was at the bottom of page 389. Okay, because we spent time on primary alcohols more than secondary. Okay. So when you look at the bottom of page 389, okay, where it says primary alcohols, okay. So we've learned this, we've seen it. So now let's read on what's actually happening here. So stage 1, simultaneous loss, and we read this yesterday, but you didn't have the book in front of you. Simultaneous loss of hydrogens called dehydrogenation from the OH group and from the carbon holding the OH produces a carbonyl group. And remember that carbonyl group can be an acid, it can be a ketone, or it can be an aldehyde. All it's saying is that you have a carbon with a double bonded oxygen. As shown in the next equation, the resulting compound is classified as an aldehyde because, and it says and, but because an hydrogen is attached to the carbonyl carbon. So when we turn the page, so step 1 is telling you that a primary alcohol oxidizes into an aldehyde. That is stage 1. Then it goes on to talk about stage 2, oxidation of the hydrogen attached to the carbonyl carbon to the OH converts the carbonyl group into a carboxyl group, or COOH. The resulting compound is called carboxylic acid. Okay? And we've seen them way back in chapter 3 when we started this, probably September? Maybe we classified these compounds. Oxidation with permanganate or dichromate proceeds from the primary alcohol all the way to the carboxylic acid without stopping at the aldehyde stage because these oxidizing agents are too strong. For situations in which the aldehyde is the desired product, the reaction can be stopped at the aldehyde stage by using oxidizing agents that are milder than permanganate or dichromate. Okay? So I don't think we really spend much time on saying, let's form an aldehyde by using an I'm trying to think of what would actually do that. Maybe sodium chromate. I think maybe isn't quite as powerful as potassium dichromate. But with that, keep in mind, primary alcohol, 2 stages when you're dealing with that KMNO4 or K2CR2O7, the dichromate ion. Okay? Now, what can happen is we may start you with an aldehyde. That means you're starting halfway through the process. Okay? And what I mean by that, when we go back to your aromatic problems, okay, that flow chart was meant to help you. If you only had that, you knew where to start, right? And that would be where on that flow chart? Right in the middle. But notice you do not always start in the middle, because maybe we're saying that you've got something like this on there. Okay? Then, well, actually that's not on your flow chart. This would be. Okay? That means you're starting about halfway through, not in the middle, but showing you where toluene is. Okay? So sometimes we'll start you with an aldehyde rather than a primary alcohol. Okay. And then secondary alcohols, that's pretty straightforward. That's not quite as complicated. Okay, on page 390, secondary alcohol oxidation follows a similar course than oxidation of primary alcohols. Oxidation cannot proceed past the carbonyl stage. So secondary alcohols, there's only one product, there's only one stage, and then you're done. Okay, and finally, we said Tertiary alcohols, that's about 3/4 of the way down. Tertiary alcohols cannot undergo selective oxidation because no hydrogen is attached to the carbon to which the OH is bonded, okay? So just keep in mind, if you see a tertiary alcohol with an oxidation agent next to it, it's no reaction. It just can't do it because it just doesn't have that, when I'll say that hydrogen next to it. So what that means, very quickly, maybe it's easier to see that. So we know this is a tertiary alcohol, X marks the spot, because there is carbon, carbon, and carbon attached to that, okay? So now, this is different than dehydration. Make sure you get that out of that you get that in your mind. It can still do this. That reaction will proceed because you've got OH and a hydrogen. That will go. This, however, that one will not, because notice that the adjoining element is a carbon here, and on this carbon is a carbon, carbon, carbon. There's no hydrogen to grab off besides that one. That's what it's trying to explain. So this would be no reaction. Okay. We're on the home stretch here. Now we got to jump forward a little bit to page 399. And this is talking about the formation of ethers by dehydration of alcohols. Okay? So it's showing you propanol, but we're going to use ethanol just because it's a lot shorter to deal with. And what it's showing you is that propanol, and then it's got a, oops, I didn't do that right. Well, I suppose if we went like this, you could say one splits up like that and the other one splits down like that, okay? So what that means is that if the temperature range is 180, you're going to get a different product than if it's at 140, okay? And I think that says that on your flow charts as well. Now, this is only for primary alcohols, okay? I think it even says that there. Oh, it just says alcohols. But in this case, it's only primary types. So, looking at that example, okay, do you get one or two products with a temperature range of 140? Is it going to be an alkene or an ether, according to what you see here? If it's at 140 degrees, you form an ether at lower temperatures. That's right. And that's one of the reasons I wanted to use ethanol rather than propanol, because what that means, for some reason, I don't know, I suppose the way I would always explain it is, I don't have one of those things that, because you use it as a percussion instrument. This is the closest I can come. But what that does, I think it's called a whip, or maybe it's a snap or a whip, and it's just something that makes a sound like that. So what that means is, notice that that flips all the way open, and you have a mirror image. Okay? What we mean by mirror image is that with an ether, does that look like a mirror image of one another? Well, look at our oxygen. Does that look like a mirror image of one another? How many carbons are to the left of that oxygen? How many are to the right? 2. So that's a mirror image of one another. That's right. Okay. And then what do we see happening at higher temperatures, or 180 degrees? Then it's just back to your normal dehydration. And then it's just up to you where you want to put your hydrogens now. Because remember what we're seeing here, dehydration, that's gone. And what's going to disappear from this carbon? What will disappear from this carbon? Well, there we go. Hydrogen. So, looks to me like you can just do this if you wanted. That would be your answer. Okay. That is correct. Okay.
So why don't you have like all four hydrogens?
Oh, this one? Yeah, you can put them in, I guess. There we go. Okay. Should have this on, shouldn't I? Yeah. This might be difficult because it's the first time you've seen it. That's the more exposure you get to it, the better off we'll be. But no, you don't need to name them. No. We just kind of do that just to kind of keep refreshing your memory, so we don't continually forget how to do that. Alrighty. Then the last thing I want to do, then we'll call it a day. What functional family do you think this is? Because I think there's examples like this on your paper that's due tomorrow on naming these. It's a kind of like a trick question. It is. Because it's a carbon with a double bonded oxygen, so it's a carbonyl group. So you either got one of two choices. It's either what or what. The one in blue here. It's an aldehyde or a ketone. So you got that limited down. Now you got a 50-50 shot. Anybody else? Well, it can't be both. You can't really visualize that it's in the middle. That's what we would associate ketones being. Thinking, well, it looks like this would be on the end. So this is kind of an exception. This is a ketone. Okay? And two ways that might help you on illustrating how we know this is a ketone. Why could that not be an aldehyde? Well, if, for instance, we were to look at this, we know that's either an aldehyde or a ketone, correct? But in order to make this an aldehyde, don't we have to have a hydrogen on there? Yes. This doesn't have a hydrogen on there. So that's why that has to be a ketone. And then finally, how many carbons are on this ring? Okay, so here's our prefix. All right. The functional family, you said, was ketone. Now, if we didn't go any further, you would be saying that this is an aliphatic carbon. In other words, it's a straight line structure. It's not. This is what type of structure? Yeah, it's a ring structure, so it's cyclo.
Will the ring structures, will they always be ketones then?
Not always, because we could make an aldehyde out of this, but because I think we've gone through enough information, I really don't want to make it worse by throwing more information at you. Okay? So, and when we see this, this would be an exception to the rule of saying that we would always say that ketones have a double bond oxygen anywhere other than the end. But this is an exception to that, because this one is going to be carbon number 1 because it takes priority because that is the organic family. Is there anything else on that ring structure? A what derivative? Yeah. And what carbon is that? So 2-ethyl. Cyclopentanone. Okay. Now, I don't know, maybe we went too fast, but the rest of the time is yours unless you have a question. Okay? And maybe we might not quite know what to ask. Okay, so, all right, we'll catch up to you next time.